right, hello everyone. Welcome to the lecture 9. All right, so today okay, so we are starting with this exercise and I let you work on it. So see you in a few minutes. So first of all, let's compute the eigenvalues of the associated matrix. So we have A, which is equal to 3 minus 2, 4 minus 1. So if I compute the trace is 2. And the determinant is minus 3 plus 8 equals 5. So my eigenvalues are given by 1/2 of the trace plus minus square root of the trace to the square, which makes 4, minus 20, and so this is negative, so I will take the absolute value and I will add I, and this gives 1 plus minus 2i. All right. So we will call lambda equals 1 minus two I, right? This will be our lambda. Okay, so now I'm going to compute the one of the eigenvectors associated with this eigenvalue. So I have to rewrite A. So A equals 3 minus 2, 4 minus 1. And I look for a V such that A minus lambda V, so sorry, A minus lambda and the identity V equals 0. So A minus lambda identity, so I recall that my lambda is 1 minus 2i. So A minus lambda identity gives 2 plus 2i. This one doesn't change. 4 and minus 2 plus 2i. All right. And then I solve 2 plus 2i times x minus 2y equals 0, which gives y equals 1 plus I x. So the simplest eigenvector that I can get is v equals 1 plus I, and I can write it as 1 plus I 0 1. And so v1 is the real part of v, and v2 is the imaginary part of v. All right. So let us remind the transformation that we did last time. So we have a matrix A. Oops. So we have a matrix A, and we have an eigenvector associated to a complex eigenvalue. And we assume that lambda equals A plus IB, which is the case for us with I equals 1, B equals minus 2, right? And then when I have that, well, you know that if I compare A1, where V1 is the real part of it, so this is the real part of AV. Because what? Because the real part of AV is the real part of sorry, let's do it. So it's the real part of A, V1 plus I V2, and this is the real part of A V1 plus I A V2. But V1 and V2 are real. V1 is the real part of V, and V2 is the imaginary part of V. So that's what I say. So this is A V1. So okay, so I just wrote a few lines to explain, right? Okay, so the real part of AV is AV1, and the imaginary part, exactly, great. So what you said is that the real part of AV is AV1, where V1 is the real part of V, and the imaginary part of AV is AV2, all right? But also, because AV equals lambda V, AV equals lambda V, so I can write that AV equals lambda V. So the real part, sorry, V is the real part of lambda V. And this is like so the complex multiplication to get the real part is the real part of lambda times the real part of B minus the imaginary part lambda times the imaginary part of V. It's like the product of two complex numbers. You get the real part, it's real part of A, etc. So I get A, so I called it V1 minus B V2. Okay, and in the same way, the imaginary part of AV is A V2 plus B V1, because it's the real part of lambda times the imaginary part of B plus the imaginary part of lambda times the real part of B. All right. Okay, so now I know that A, so let's write V1 V2, and this I know that's equal to AV1, and this one I know that's AV2. So let's write this matrix. V1 V2 is a matrix. It's the matrix whose components are the vectors V1 and V2. And then I write the product. So now I put this matrix in this side. And I want to write a matrix such that I have equality. And so this is the product of two matrices. If I know that AV1, when I will make the product of this matrix times this matrix, here I have to write the right column. It will be, so because AV1 is AV1 minus BV2, I will write here IA minus B, which is the product of matrix line times column. And here, because AV1 is that, and to get AV2, I will work with the product of the matrix times the second column. And I want that to be AV2 plus BV1. So I have to write that. So if I call this matrix P, this is a matrix P, and I will call it H. Okay, so here I just took that and wrote this equality as a matrix equality. Okay, so I got that AP equals PH, which means that A equals PHP minus 1. So we have AP equals PH with H equals the real part of lambda, which is 1. Here you have minus B. Here B, which is the imaginary part of lambda. Here you have your A. And the matrix P is V1 as the first column and V2 as the second column. All right. And so if I want to compute the inverse, I just have to do 1, 1, 0, minus 1. Okay, you can check. This is the inverse of. And so, which is interesting that is that. So you start with x prime equals ax, but you have a, which is a is p h p minus 1. And so you get p minus 1 x prime equals h p minus 1 x, which gives y prime equals hy with y equals p minus 1 x, which is equivalent to x equals py. Okay, but now let's compute the solutions of y prime equals hy, and let's draw it. Let's draw this solution. And then to obtain x is just a linear transformation. So let's compute the solution of y prime equals hy, which is y prime equals 1, 1, 2, minus 2, y. So I wrote it again. So x prime equals x plus 2y, and y prime equals minus 2x plus y. So last week I did it with a and b in the general way. So let's do it with the numbers, just as an application. So so it will be simpler to write it in the complex way. So I will write here x plus I y prime by summing up the two lines, and before I multiply the second line by I. So I get x plus 2y plus I minus 2x plus y. So as you can see, I will get x plus I y here plus 2I So let's do it in. So what I get is x plus IY. It's okay now. It remains plus 2 plus 2. So I get here what I don't have, the y minus I x. So yeah, and now I do x plus I y plus 2I, and here, so it's minus x minus I y, and so I can just put, instead of a plus, I put a minus here, and I got that. So finally, if I call it z, I call this expression z, I got z prime equals z times 1 minus 2i. And this I know the solution is z of t equals z0 exponential t So, and then with this expression, we can draw the solutions. Because, so this part will make the solution rotate in the negative direction. And this part will make the norm of the solution at each time t grow exponentially. So finally, I get is something like that. Something like that. All right. And so to illustrate what we did, we are going to run some numerics. So here, as it's a program, C++ program, and we just implemented the Runge-Kutta 4 method to solve the equation. So as you can see, we have A equals 3, B minus 2, C 4, D minus 1, which corresponds to the matrix A. Right? So I'm just running this. All right. So as you can see, we have not a number. This indicates that actually the numbers are very large, which is not so surprising because we have an exponential growth. All right. So now we are plotting the results. So let's have a look at this file. All right. So all right. So now we are going to have a look at the solutions. All right. So this is the This is the solution. All right. We can also compute the solution of the system y prime equals hy. So to do that, I'm going to change a little bit this program. So it's here. So B was 2. C was -2. And G was 1. And instead, all right. So this line here correspond to the change. So I take an initial condition. Then this initial condition, I multiply it by the matrix inverse of P. That's my x0 here and my y0 here. All right, so now I'm going to run this program. And just so now I'm running the program, the system y prime equals hy. Right? So again, not a number because the number are too large because I have an exponential growth. And here, so let's change. Now, what I want to plot, so it's a little bit different. So I'm going to plot the solution of my original equation and then the solution of my simplified system. No, that's a problem. Don't know why. So maybe I made a mistake somewhere. So here I forgot to change my initial conditions. So My initial condition, in fact, is x0, y0. So now I did it. Let's run it again. So there was a problem. We did a small mistake. I did a small mistake. When I wrote the matrix H, I wrote 1, 2, -2, 1. And it had to be 1, -2, 2, 1. And so that's why we got a problem with the numeric. So it's good to do the numeric. So let's change that. So in here, I'm changing that in the numeric. So it's 1 -2, 2, 1. And I run it again. Okay. So now I'm going to plot. I'm going to plot again. So the solution of the original equation and the solution of my system y prime equals hy with the right h. And let's see. So system. All right. So now you don't see? That's right. Yeah, I have to share. Let's share. It's weird. So that's what I obtained. So after correction, now with the right h, so in blue is the solution of the system y prime equals hy, and in red is the solution of the system x prime equals ax. So what I'm going to do now is that I'm going to plot, instead of the solution of my original problem, I will plot also p times the solution of the system in y. Okay, so now I'm plotting the solution of the system in y and p times the solution on y. And I should recover the solution of the initial problem. Okay, that's right. That's the same. Yeah. All right, so provide numerical simulations of system 3.10. We did it. So we're good with that. And so now we move with other cases. So for example, if we have one eigenvalue which is 0. So in order to understand what's going on in this case, I suggest this equation to solve. Okay, so let's do that. So we are looking at x prime equals, so it's x minus y, and y prime equals x minus 2y, right? Okay, so you can see that the matrix has a determinant 0, which means that lambda equals 0. 0 is an eigenvalue, right? So, but let's do the job as usual. So my matrix here writes 1, minus 1, 2, minus 2. So the trace is minus 1, and the determinant is is 0, of course. I just said that. All right. Yeah, thank you. So my two eigenvalues are lambda 1, 2, the trace plus minus square root of 1. So I can say, for example, lambda 1 equals minus 1, and lambda 2 equals 0. Let's compute the eigenvectors. So A minus lambda 1 identity is equal to 2 minus 1, 2 minus 1. So 2x minus y equals 0 gives y equals 2x. So I can choose v1 to be 1, 2. All right? Okay. Next, v2. So 1 minus 1, 2 minus 2, xy equals 0. So gives x minus y equals 0. So y equals x. So I can choose v2 to be, sorry, 1, 1. But when I solve that, I solve the stationary solutions. When I solve, so what's that? So this. I don't know why. Okay. So when I solve, when I look for a eigenvector associated with my matrix A and the eigenvalue 0, I'm looking for stationary solutions. All right. So what's the meaning? Is that I have a lot of stationary solutions here. So for all beta 1, 1 is a stationary solution. Okay, that being said, I can write the solution. We already did that. So if I choose x of t to be alpha exponential minus t v1 plus beta v2, I have all the solutions. Okay, now let's draw. Let's draw the solutions. So all right, so this is y equals x. So when I pick up a point here, it's a solution of the ODE. Right? Now I'm drawing the other eigenvector. Let's draw it in black. So 1, 2. So it's not good. I wanted to be in black. Oh, where is it? So here's the solution. If beta equals 0, then the solution goes to 0. Okay, now what if I choose a pick up an initial condition here? Where does it go? So from this expression, so at time t equals 0, here this point as for coordinate alpha beta, and as t goes to infinity, this term is going to 0. So at the end, the coordinate for t equals infinity is beta times v2. But as you can see, it will go parallel to this one. So it will go like that. Yeah. You have to think. All right. And if I pick up a solution here, it's go like that. And okay, whatever. So it's parallel, right? So they are all parallel. So for a linear system, if the determinant is non-zero, you have only 0, 0 for stationary solution. But here, since the determinant is 0, you obtain a lot of fixed points, and for each initial solution, you're going towards a stationary solution on one of the stationary points. All right, so here is the drawing corresponding to this solution. So next, okay, now, so it's very easy. This one is very easy, but we have to draw the solutions, right? So it's when you have two equal real eigenvalues, and you can diagonalize the matrix. So in fact, the matrix is diagonal. Right? All right, so let's consider this system. So you have that x of t equals x0 exponential minus t, and y of t equals y0 exponential minus t. So now, if I want to draw that, so let's start so for example, let's start with a special solution. So if y0 equals 0, then y of t is 0, and x of t is going to 0. So I'm here. If x0 is positive and I'm here, x0 is negative. If instead I choose x0 to be 0, it's that one. Now pick up x0 and y0 wherever you want. For example, here. So here x0 is positive and y0 is positive. But you get that, what do you get? You get that y of t equals x of t divided by x0. So it's, yeah. So it's y is a linear function of x, and with this coefficient, which is given by, so the solution now is just that. So the solution is that, and I draw also the other part corresponding to minus x0 and y0. So you could see directly that, because the solution lie on a vector, and then the coefficients are going to 0. So again, other solutions. So everything's like that.